A majority of the work happening inside the cell are in the form of chemical reactions. So let us view the concept of free energy in terms of its role in chemical reactions. Now, it's important to note that all chemical reactions happening in a cell are reversible in nature. Meaning to say that as reactants react to form the products simultaneously also react to form back the reactants. Now, this forward or reverse direction of chemical reactions are actually described according to how fast they happen. For example, how fast do the reactants become the products? Or, at the bottom arrow, how fast do the products become the reactants? Notice here in our expression, K sub 1, and then there are two brackets, bracket A inside closed brackets, and then B inside closed brackets. This indicates the concentration of the substance A and B. So the rate of forward reaction, K sub 1, is actually dictated by the concentration of A and B, which are the reactants. Likewise, the backward rate of the reaction, which is K sub 2, is related to the concentration of the products, which are C and D. And as what you might have already predicted, the higher the concentration of the reactants, the more forward the reaction is going to be. So notice here our arrow going backwards is now shorter, indicating that the forward reaction is greater because the concentrations of A and B are greater as compared to C and D. If the reverse is true, the reaction will be mostly backwards or in reverse. So this time, the concentration of the products is actually greater than the concentration of the reactants. However, there is a sweet spot, as illustrated by the first illustration, also shown here, wherein the two arrows, the rate forward and the rate backward, are equal. We call this state equilibrium, meaning to say the concentrations of the reactants is equal to the concentration of the products in equilibrium. Then we have a ratio called the equilibrium constant. The equilibrium constant is actually unique in different types of chemical reactions. So, meaning to say, a different kind of chemical reaction, let's say the formation of sodium chloride from sodium and chlorine, has its own equilibrium constant, or K sub EQ. So K sub EQ is equal to the ratio of the rate of the forward reaction and the rate of the reverse reaction. So it's a fraction. So we will go back to this concept later on at the end of this video. Similar to chemical reactions, we also have a dissociation constant. So this is similar to the equilibrium constant, but this time dissociation constant. And here we are not necessarily talking about chemical reactions, but we are talking about the how much is the tendency for two particles to stick, usually non-covalently. So meaning to say it can be an ionic bond, it can be a hydrogen bond, it can be a van der Waals bond. So here we have a similar setup. On the left, you have here sort of a chemical reaction although not all of these will be chemical reactions, showing the dissociation of AB to become A plus B. And understandably, if the concentration of AB is very high, as shown in the upward arrow, as compared to the concentration of A or B, then this reaction is going to move forward. But if the concentration of A plus B is greater than the concentration of AB, then this reaction is going to be predominantly backwards. And here on the right, you have the dissociation constant, which is again unique to different types of situations. So here's an example situation where dissociation may happen. When enzymes actually work with their substrates, they usually need to bond to their substrates non-covalently. So let's say our enzyme here is the one in red, and our substrate is the one in blue. So if the concentration of the bonded red-blue, which is our enzyme substrate complex, is greater than the concentration of either the red substance or the blue substance, then this reaction is going to be moving forward towards the dissociation of the red-blue complex to become separate red and blue substances. And the same is true if the concentration of the separated red and blue substances is greater than that of the red-blue complex, then this reaction is going to move backwards towards the formation of the red-blue complex. So I have here a repeated picture of our first slide, and on the right, I have here the relationship between our Gibbs free energy, okay, I hope you remember G, and our equilibrium constant. Here on the top, we have an example of a chemical reaction wherein the free energy is negative 8.2. Remember, if the free energy is negative 8.2, what is this reaction going to be? Exothermic? Endothermic? Could be neither. When your free energy is negative 8.2, then this reaction is very spontaneous. And then look at the equilibrium constant here on the left, 10 to the power of 6. That's a very large equilibrium constant. What does that mean? Look at the equation for the equilibrium constant. The numerator will be the concentration of the products, and the denominator will be the concentration of the reactants. Meaning to say, the equilibrium of this reaction with delta G, that's negative 8.2, is only possible when the concentration of the products is way above that of the concentration of the reactants, 10 to the power of 6. Meaning to say, the reaction will always tend to move, in this case, to the right or towards the products. Now, isn't that what a spontaneous reaction is? It just moves forward towards the product. Here at the bottom, we have another reaction with a very high free energy, 8.2. If the free energy of the reaction is 8.2, then that reaction is not spontaneous at all. Meaning to say, it won't just happen by itself. Now look at the equilibrium constant of this reaction. It's very low. Meaning to say, if we use the equation of shown here on the left, in a non-spontaneous reaction, the equilibrium is when the reactant's concentration is very high as compared to the concentration of the products. Meaning to say, the reaction won't even move forward that much because it will already reach its equilibrium even with just a very short or little reaction. So meaning to say, what you observe is as if there's nothing that's happening to the reaction because it's non-spontaneous, because its free energy is very high, it's positive. So consider for a moment this slide and maybe review for yourselves a bit and understand for yourselves a bit what I'm speaking here about, what these numbers mean, because these are very important for you to get in order to understand how enzymes work.